Good morning everyone. Today I'm going to share with you guys how I have performed the LSTM calculation, which is handwritten, and I will be explaining you all the theoretical concepts behind this. Before going into the numerical part, I'll just explain few things about this diagram first. So, what is the next word prediction? Next word prediction is a language modeling task where, given a sequence of words, the model will predict the most probable next word. Remember, this is probabilistic in nature and not deterministic. So here, as you can see, there are the embeddings which have been used along with the hidden layers. So we'll go into that in detail, but as you can see, the next token at the end is been getting predicted with the use of the embeddings, which is, you can say, kind of an input to this LSTM network. So what is a vocabulary? Vocabulary, as you can see, there is a vocabulary size mean. So what is that? Our language model only knows the 5 unique tokens. So in grammar, there are over millions of words. But for our simplicity, we have used a grammar which has only a vocabulary size of 5, meaning it only knows the vocabulary language is with 5 words, 5 unique tokens. So this is an example. What is the tokenization? Tokenization means the conversion of the words into numerical IDs. So this is, as you can see, the LSTM model will not understand the grammar, but it will understand the embeddings. So what is the embedding layer? So neural network cannot process token IDs directly. So we convert the token IDs into dense vectors. This is called as word embedding. Embedding dimension is equal to 2. As you can see, this means that each word is represented as a two-dimensional vector. And embedding matrix, as you can see later, we have been computing using 5 by 2. How is it 5 by 2? Because each row represents one words vector. This is word number 1, word number 2, up to word number 5. So what is the purpose of embedding? It captures the semantic meaning and it makes learning of the network possible. And it also converts the discrete tokens info in the continuous space. So what is LSTM? LSTM stands for long short-term memory. Long short-term memory. So as you can see, this is an animation. I think it will not work here. Okay, but I will just summarize it. It is a special type of recurrent neural network, and a simple recurrent neural network suffers from vanishing gradient problem and cannot remember long-term dependency. So there is a cell state, as you can see here, and this is a short-term memory network which is represented with some non-linear functions, and this cell state is helping to manage the forgetting state from the last state. So it is used as to store the information from the past state. So you can remember it like that. And what is the hidden state? Hidden state is the short-term memory of the network. So all the information, as you know, in recurrent neural network, this H3 was responsible for the information from the last two hidden state, and it was having a lot of information within it. So hidden state is the short-term memory of the network. It captures the information from the previous time step. What is the cell state? Cell state is a long-term memory of LSTM. As you can see, this is the cell state, which is denoted by CT. So what are the gates in LSTM? LSTM is just three gates. One is a forget gate, one is the input gate, and the other one is the output gate. So these are the three gates which are being used in this network. So each gate is a neural network layer. And the forget gate is used to decide what information to remove from the previous cell state. Then we'll check about the input gate, and you can see I have solved that here. Forget gate, input gate, and the output gate. So it is also uses non-linear functions like sigmoid function and the candidate cell state. As you said, we had used it for using updating the long state memory. So there is a cell update equation. We'll see that in a moment. And the concatenation is just combining two matrices one after the another. So this is concatenation. Now, as you can see, after a certain level, we have said we are applying tan h and all that thing, which is non-linearity function. But after that, you can see at the end when we are completing, you can see applying sigmoid kind of thing. You can see somewhere we are written applying sigmoid. This is non-linearity function. So also you might see there somewhere it will be called as a softmax. Now what is this softmax? So softmax is converting this logits matrix into probability, because if you see this negative values do not denote relevant information to your network. So how to bring it between 0 to 1? So softmax is a method which will bring the probability value between 0 to 1. And that is it. I think we have long information enough to start off with the explanation of this numerical. So what is it? So in this assignment, we'll have manually compute the next for prediction using a handwritten LSTM. So we were given the vocabulary size of 5, embedding size of 2, hidden size of 2, and the context size of 3. And so we'll take three tokens as input, pass them through first of all the embedding layer. This is the embedding layer. Then we have the LSTM layer, then the logits layer, which is comprising of the hidden set, and then we apply softmax on it. And then we finally predict the next token or the next word. So what is the token embedding? Since vocabulary size is 5 and the embedding dimension is 2 as you can see above. So what we are doing, the embedding matrix must be of size. So the 5 denotes the number of rows and 2 denotes the number of columns. So what does it 5 denote the vocabulary size? And what does it 2 denote the embedding dimension? So a 5 by 2 matrix is being created which is called as an embedding matrix. So each row corresponds to one token in vocabulary as I explained you earlier. So assume these are the three tokens which are available with us. So first of all, this is the token embedding. So you can say this is the embedding. So how many rows? So it will be having a dimension of 2 and 1, 2 rows and 1 column. So as you can see, it is shown here that is 2 rows and 1 column. So after embedding layer, each HT will be a dimension 2 and it now will compute the LSTM computation. So we are knowing this that we have to compute every step. We are initializing something known as the weights of the forget gate, the input gate, the output gate, and the cell state. So these are the random weights assigned initially, which is saying before the training period, and we'll just weight matrices with biases. Now biases are assumed 0, but it's not always 0, and it has a dimension of 2 rows and 1 column, not exactly what you can see in the weight matrix, which I have is 2 rows and 4 columns. So this is one of the things you should need to remember, and all gate outputs vectors of size equal to hidden state 2. So LSTM equation. So for the time step one, so we will be doing for 3 steps. So this is time step 1. So what we'll do is for time step 1, first of all, we will concatenate x0 with x1. This is the first step. This is the hidden state 0 concatenated with the input embedding 1. So after doing this, I have shown you in the easier way that how we are concatenating. Then we are going through the forget gate. So forget gate calculation is very simple. WF, which we have already assigned a value, random value. So we are going to multiply it with Z1, and the Z1 is nothing but this concatenated matrix, and we'll just compute matrix multiplication, normal matrix multiplication, and after doing it, so if you see 1 into 0 gives 0, 0 into 0 gives 0, 1 into 1 gives 1, and 0 into 0 gives 0. So as it is, you can see this with this with this. I will check if I could edit also calculation of WF into Z1, then applying the sigmoid function, and basically the sigmoid function is used to apply non-linearity to these values, and then we are computing the input gate similarly with the formula of WI into Z1, then applying sigmoid, then similarly output gate with W0 and Z1, we are doing the normal matrix multiplication and we are applying the sigmoid to it, and the candidate cell which is WC into Z1, and after applying the sigmoid we get all the things. Now what is cell update? This is something a new formula. What is it? So the generalized formula is CT equal to FT in that symbol is nothing but the element wise multiplication. So now in the steps above you have seen matrix multiplication, which is just multiplying each row to each column, but here in element wise multiplication we are going to multiply elements by elements. So if it's this were to this, so we are going to multiply element by element, and as you can see the formula, it is first this, then compute this, and then adding both of these values, and then we are getting the C1. What is C1? C1 is the cell state, that is a cell update. So what is a cell update? And the hidden state, what will be the hidden state value? So here there is a mistake. This shouldn't be a multiplication. Then this again a element wise multiplication operator. This will be element wise multiplication operator, which will compute the h1, which is the hidden state. So this completes the time step 1. So which concludes now the similar procedure will be get followed. Now here as above you can see we had used h0 and x1. Now similarly for the next step we are going to update that and use h1 and x2, and we'll concatenate them. After concatenating we are using to use the forget gate. The forget gate will help the same formula WF into Z2, and we get sigmoid, and then here again the input gate, the candidate cell, and the output gate. And after computing this, we are going to do cell update. Again, this is element wise multiplication. We are following the same step. Till when we will follow? Till time step 3. Why we are going 3? Because we have 3 input embedding. So we are going to compute it for 3 times. So this is tan h. This is the adding non-linearity to our candidate cell, and we are going to compute h2 with the same formula. And then time step 3 similarly. Now let's go till the hidden state of this. So this is what we will reach after doing the same step as we have explained earlier till the time step 3. Now what is final logic? So let us take the final hidden state, that is H3, which is now H3 because of the fact that we have three embedding. So what will he do? It will try to predict the next word. How will it try to predict? So it will take the output weight matrix and the bias matrix, which we had 0 initially. So we will use a formula which is W out into H3 plus B out. Now B out is 0. So technically I have not shown it here, but we can add B out if there was some bias initialized by me earlier. So here we are going to compute this value. And what will be the dimension? So W out is what? 5 rows and 2 columns. H3. H3 is what? 2 rows and 1 column. So it will be 5 cross 1. I can I think you have understood what I'm trying to say. So this is 5 cross 2, this is 2 cross 1. So and we do multiplication. So matrix multiplication will discard the row and column property. So it will be 5 cross 1. So after doing this, we get the value of y. And what does this y show? Each value correspond to the one vocabulary token. So you know there were 5 vocabulary tokens. The 5 vocabulary tokens, as we have initialized earlier, we have got 5. Now, but you cannot say which one is more good to select as a next token. So this is where softmax comes into picture, because you can't say these negative values to classify whether this is too good or too bad. So softmax is probability distribution over the 5 vocabulary words. So it will give you that, and using its sum and finding out the probability, the highest probability which we got is on the third vocabulary. So you can say that we can say easily that it's been easy to classify that the highest predicted next token is the one with the highest probability, so that is token T. So this is how the LSTM network is working, and this is how it is expected. So I will show you the animation part which I couldn't show. So as you can see, first of all, so we'll just, so as you can see, the above one is showing you the long-term memory, this is cell state. Then this is the hidden layer which is passed to the input forget state gate, then the input gate, and then finally after processing everything, it goes to the output gate, and then we get the next hidden state along with the cell state. So these two states are important. The cell state is responsible for the long-term context, whereas the hidden state is passing the information to the next hidden state. So how the number of hidden states will get passed part by part. So this is what the LSTM network does. So thank you very much.